Good morning, everyone. Welcome to the second lecture on gravity. In today's lecture, we'll be talking about a few more concepts that are related to the topic of gravity, and they are about gravitational potential energy and the idea of gravitational field. Okay, so let's refresh what we studied in the last class. In the previous lecture, we saw the Newton's universal gravitational law. It was defined as the factor F force is given by G m1 m2 by r square. Okay, and we said that this G, capital G, is a constant. It's known as the universal gravitational constant, and the value for G is given by 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Okay, so this law of gravity is telling us the attractive force that will exist between any two particles in this universe. Okay, so any two objects that have some mass m1 and m2, they will have a force of attraction between them, and that is given by this quantity right here. Okay, r is the separation of distance between the two objects. Okay, and we also looked at the case when we have more than two objects, then you can use the vector decomposition and just add the forces that are acting at a given point or on a given object. Okay, so again, this law is an inverse square law. Okay, so the magnitude of this force at large distances is very small. Okay, and in fact, if you look at the comparison between the four forces in nature, here you have the relative strengths for two protons in the nucleus. You can see that the gravitational force has the lowest magnitude. It's about 10 to the power minus 38 orders of magnitude, and that compared to the nuclear force is a much smaller value. Okay, so that's what we meant by gravity being the weakest of the four forces. Okay, so later on we will talk a little bit about gravitons. These are the field particles that are responsible for this force to cause the interaction, and there is still search going on for these gravitons, and we haven't found them yet, right? So we have found photons and gluons and other stuff, but we haven't found gravitons yet. Okay, so we also looked at the difference between this capital G and small g, and we said that the small g is acceleration due to gravity, and it is related to the capital G in this form, right? So the small g is capital G times the mass of the earth divided by radius of the earth square. So any object that is present on the surface of the earth, we have always used the notation that the force that is acting on the object is mg. We use that many times in many of the problems. Okay, so if the distance r changes, then your small acceleration due to gravity will also change. Okay, so let's look at that idea of gravitational potential energy, because just like I was mentioning about the force being written as mg, we have always written gravitational potential energy as mgh. Okay, for any object at any location. So how do we relate both of these concepts? Okay, so the definition for gravitational potential energy is that it is the amount of work one has to do to bring a certain mass m from infinity to that point P where you are calculating your gravitational potential energy. Okay, so for example, you have earth here, all right, and you want to find what is the gravitational potential energy at this point P. Okay, so how will we denote this notation? We will look at infinity, and we will say that the amount of work that is done to move the object all the way from infinity to this point P is where we have to keep our mass m. Okay, and the amount of work that will be required to do to move the object all the way from infinity to P is the amount of potential energy that it will possess. Okay, and by notation, what we always say is that this potential at infinity will be 0. Okay, so all the values of your potential energies will become negative, because the highest most point, which is at infinity, is regarded as our scale of 0. Okay, so again, if we are trying to move an object from p to infinity, similarly gravity is trying to move an object from infinity to p. Okay, so the notation that we use is that if some person is doing the amount of work that it has to do to move this object, then the force that we'll be using is this value g me m by r square. Okay, and like yesterday we were noting that there will be opposite force acting on this object, and so at the same time the gravitational force will be minus of this value. Okay, so the gravitational force will be written as minus g mass of the earth times the mass of the object divided by r square. Okay, so simply stating that if we move away from the earth, right, the gravitational potential energy has to increase, right, because you have a scale of 0 here, okay, which is the highest most point, and then all the values here are negative in your scale, all the values here are positive. Okay, and suppose this is the surface of the earth here, so it is another negative value, but when you're moving away from the surface of the earth, then you are going towards a positive value. Okay, so the gravitational potential energy will increase as you move away from the earth, or if you move an object from the earth surface to some certain height. Okay, and if we do that, we have used the notation that the gravity will be doing the negative work, right? So if I move an object from this position here all the way to this position here, I am doing positive work, whereas gravity will be doing negative work in that instance. Okay, so that is governing the way we use the notation of the plus and minus signs when we are describing the work being positive or negative. Okay, so remember, gravity always does negative work. Okay, so mathematically, you can write it down as your force times distance formula. Work done to move from infinity to certain position r will be given by this formula, right? Infinity to r integral of f dot dr. Okay, so we just plug in our value here, which is m times meg by r square. That is the value of the force. And if you take the integral, we have mass of the object and mass of the earth and g, these are constants. Okay, so they will come out of the integral, and all you have to do is you have to do integral of 1 over r square. Okay, so 1 over r square is nothing but minus 1 over r. Okay, so here you can just plug in your limits. So the first value will be minus 1 over r, and the second value will be 1 over infinity, and 1 over infinity is just 0. So you are left with just 1 over r. Okay, so this term, which is the work done, is your gravitational potential energy, and it is given by this value minus m times mass of the earth times g divided by r, and this small m is the mass of the object. Okay, so this is the 1 over r relationship. So this green curve is showing how the 1 over r relationship looks like as you move and increase the value of r. Right, note that 0 is the maximum value and all the values are negative. Okay, and certainly somewhere along the line at the radius of the earth, then you have to just substitute the value of r of the earth here, and you will get the potential energy at the surface of the earth. Okay, and by convention, again, you have to remember that at infinity, as r tends to infinity, this value of u will tend to 0. Along this curve, now suppose I move between 2 points. Suppose I move between point A and point B. Okay, so we are doing some work in moving an object from position A to position B, and we always say that if something is going away from the earth, it is gaining some potential energy, and that is what we write as mgh. Okay, so let's take h as the height, that is the distance between these two positions A and B. Okay, and those are position r. Okay, so now if you look at this curve, you have certain potential energy at this location A. Okay, and you have certain potential energy at location B. Okay, and note that the potential at B is higher than potential at A. Okay, so we want to find the relationship of this expression. Okay, so again, our convention is correct. Gravitational potential energy increases as we move an object from height A to height B. And from our expression, we can write that the potential energy at B will be minus m, whatever mass is at that position, times the mass of the earth, times g divided by r plus h, right? Where r is the, let's take r as the surface of the earth, and so you are moving certain height. Okay, so then you have r plus h as the term for your potential energy at B, right? And at for potential energy at A, it will simply just be minus m me g by r. Okay, so that is the value of the position from the center of the earth. Okay, so this first expression, which is u of b, we can simplify it further, and we can write it down as minus m meg by taking r outside and writing it as 1 plus h over r. Okay, and here we can use an approximation and say that, let's say that the height that you're moving is much smaller than the radius of the earth. And no wonder, I mean, it is true. If you are just moving, let's say 1 or 2 meters or 10 meters, it is much smaller than, you know, the radius of the earth, which is in some thousands of kilometers. Okay, so this expression, we can use the Taylor series expansion here. Okay, and the Taylor series expansion simply states that if you have a term which is 1 plus x raised to some n, like this, then you can, for a good approximation, write it as 1 plus n times x. Okay, and the better the approximation will be as this x is smaller and smaller. Okay, so the smaller the value of x, the better this approximation will be. Okay, so here we have the expression of 1 plus h by r raised to minus 1. So our n is minus 1. So what we can do is we can write it as 1 plus nx. So we'll have 1 plus minus 1 times h by r. Okay, so there is a good approximation that you can just simplify this term and write it as this term right here. Okay, so in a Taylor series expansion, you have higher order terms, but you can neglect the higher order terms. Okay, so that is what we are doing. We are using Taylor series expansion. Okay, and neglecting higher order terms. Okay, so again, so you will get an expression that looks something like this: minus m me times g by r times 1 minus h by r. Okay, and then you can just multiply it inside, and the first term will be minus m me g by r, and the second term will be minus, and minus will become a plus sign. So you have m me g h by r square. Okay, so now you have the two expressions u of b and u of a. So you can just calculate the change in potential energy, which will be possessed by the mass m when we move it to certain height, you know, b, and we can just subtract a from b. Okay, and if you do that, you will see that this term here and this term here gets cancelled. Okay, because they are the same. All right, so we are left with this expression m meg by r square times h, but note that this expression right here is the value of this small g. Okay, that is what we had gotten before. Me times g by r square was your small g, right? This is the mass of the earth, this is the radius of the earth, right? And so we have the same expression here. You have mass of the earth, and this is r is the radius of the earth, because this is the surface of the earth, the position where we are standing here, a. So you get the value as mgh, and this is the expression we have been using all the time. Okay, so it was nothing wrong that you were doing before, except that you didn't know where it was coming from. Okay, so it was just an approximation that we are doing every time. Okay, so you have to keep that in mind. All right, so a much more better expression for the gravitational potential energy is to use an expression of this form, right, which is g m of e divided by re plus h square. And that is what we were trying to discuss yesterday, that this g value will change depending on your height from where you're measuring on the earth. Okay, and we also looked at different altitudes, and the value of g changing with respect to all these different altitudes. Okay, because note, this h now is a much higher value, and so it will have a significant effect on your value of g. Okay, next topic that we want to talk about is gravitational mass. Okay, so until now we have looked at mass. We have not thought about there might be more than one kind of mass. Okay, so there is the idea of gravitational mass, and there is the idea of inertial mass. Okay, and how do we understand both of these, right? So if you look at this equation, we have force is equal to mg. Okay, now we are saying that there is a force that is acting on this mass, and this g, which is that big expression of capital G, whatever, it can vary. It can vary from place to place, location to location. Okay, but important thing to understand here is that when the force is acting on this object of mass m, there is no requirement that this object is moving, right? So if the object is stationary, standing at some position or fixed at certain position, there is still a force acting on it. Okay, so it does not require an object to be moving. Okay, so it's a completely different way of understanding how a force is acting on an object. Okay, so this mass that has to deal with the gravitational force, we define it as a property of an object that is responsible for the gravitational force it exerts on another object. Okay, and that is what we are saying is the gravitational mass. Okay, so if there is some mass that an object is possessing, okay, because of that mass it is creating a gravitational force on another mass. Okay, and that is a completely different way of interpreting what the mass is. Okay, because remember previously we had said that we have our equation of F is equal to ma. Okay, and here we say that this can also be written as dp by dt, right? So that is change in momentum, so things are moving, and if there is no movement, then certainly this is zero, right? But you see, so here when we are defining mass, it has to do with the motion of the object, and we defined as this mass as being inertial mass. Okay, and we said that this is the property of an object that measures its resistance to acceleration. Okay, so that's a completely different idea conceptually in physics. Okay, so when we are talking about gravity, we have to remember that we are talking about gravitational mass. Okay, and what is this mass helping us to do? This mass, small mass m, it is helping us to determine the strength of the gravitational attraction between one object and the other. Okay, so conceptually it's a completely different play field, it's a completely different idea than thinking about objects moving and you're applying a force and then there will be some acceleration, change in momentum. So all these concepts, they are very, very different from when we're talking about gravity and gravitational mass and the force of gravity. Okay, and of course this is not an easy thing to realize. Okay, even Newton had a lot of issues with the gravitational force, because it's a force that is acting on an object at a distance. Okay, so it is not something that is in contact with some certain object. So it's very spooky thing, right? So you cannot show um, the existence of the force by just looking at one object colliding with another object and things moving in certain directions, because in our day-to-day life, in our day-to-day experience, that is much more easy to comprehend. Okay, however, now you are having this gravitational force, right, which is acting at a distance far, far away from where it is originating. Okay, so it's a much difficult concept to actually comprehend than what we have been taking for granted. We'll introduce now the idea of gravitational field. Okay, so uh, we have used this law of gravitation, okay, to explain a lot of things. We are trying to explain how planets are moving. We are trying to explain how tides are being formed on earth because of the relationship with the moon, and the 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 whole idea of how two objects interact with each other without being in contact. Okay, so that is what we are trying to get at. Objects are interacting. Okay, and they are not in contact. Okay, so you see here again, so we are going to a different regime. We have just transitioned from something which always, we were talking about friction. So friction objects have to be in contact. Okay, and we were talking about inclines, and we were talking about, rotational motion, something going around to right, and all those things. And we talked about collisions. So everything, the objects were touching each other, and it was a completely different way of thinking about them. Now we are talking about objects are interacting. They are exerting forces on each other, but they are not in contact. Okay, so then you might ask this question. Suppose you have an object like this here. Okay, and we said that if there is another object here, okay, so then there will be some gravitational field, and there will be some force that will cause this object to get attracted towards this object here, right? So we can call this mass m1, this we can call this mass m2, and we can also take the idea that this is the mass of the earth. Okay, so now what I'm going to say is, what happens if there is no mass here? So if there was no mass here, would there be some attractive force existing at this point here at question? So that is the thing we are trying to say. Okay, so here what we do in physics is we try to introduce the idea of a test particle. Okay, and what we say is, if I keep a test particle of some mass m here at this position p, what will be the uh, result of that interaction with a mass m1 that is already existing here? Okay, that, or let me restate this statement. Okay, now you have earth and you have the moon. Okay, so there is some gravitational force acting between them, and that is making the moon go around the earth. Okay, so if there was no moon, the question is, will the earth still be applying some gravitational force at the position where moon is existing? And if any other object came at that position, will it still feel the same force that moon is feeling? See, what I'm saying is, earth is creating a gravitational field. Okay, and this field that the earth is creating, how will that field look like? Okay, so that field may look like something like this. Okay, so if this is the earth, that field will look something like this. Everything that comes in that field will try to be attracted towards the center of the earth. We know that. We talked about it when we thought about the Newton's apple, that the apple is trying to go towards the center of the earth. So we can imagine that there is a field existing around earth. Why? Because of the mass of the earth. And this field is going to cause any object that comes in the vicinity of this field to go towards the center of the earth. Okay, so what we are trying to say is that the object that is being attracted, that doesn't matter. The test particle at this position p does not matter. Okay, whatever you keep here, or let's move it closer to the earth. Okay, let's move it somewhere here. Whatever you keep here, any object here, it will feel this positive attraction towards the earth. Okay, so regardless of whatever there is here, it has to have whatever mass it has. Okay, so the field is always existing. Okay, and we can refer to this field that is being created by the earth as being the source field from this source particle. Okay, so we have a source field coming from a source particle, and we have a test particle that we can say that if I keep the test particle here, what will be the gravitational force that will exist on this particle? Okay, and simply stating, we have already written that force is given by m times g. Okay, and so now we'll define, let's take g as this f of g divided by m. Okay, and this g is my gravitational field. Okay, so what am I doing here? if you look at the mathematical expression, what I'm doing is I am taking one of the masses and cancelling it. So I have m by m, so that will get cancelled. So I'm getting just gme by r square term, and I have the position vector here. Okay, that is describing where the field is going, right? So for Earth, it is always pointing towards the center. Okay, so this is my expression of the gravitational field. Okay, regardless of the mass, I have cancelled the mass. Okay, and that is what my expression is. Okay, and you can think of it in another terms. Okay, I can write it mathematically like this, that a gravitational field at a point is defined as the force experienced by a unit mass placed at that point in the field. Okay, because you can see this expression here. Okay, so you have f of g. All right, so we write it as g m times me by r square. Okay, and we have the position vector here. Okay, so if I consider m to be of unit mass, what will I get? I will get the same expression here, g me by r square. Okay, so it's the same thing. We are saying that g we have defined as the gravitational field is basically your force that is experienced by a unit mass placed at that point in the field. Okay, so that will kind of give us an idea of, regardless of whatever test particle or test mass you put in the vicinity of a field that is already existing, what kind of force will act on it and what kind of motion it will do. Okay, so it is a very similar concept to what you have seen in electricity in your high school. Okay, we introduce electricity and magnetism by describing that we have the positive charge and negative charge in electricity, and the field lines of electric field go from one position to the other, right? And then we again describe that, forget about this test charges, let's say the electric field is always existing, and now in this electric field, if we put a test charge which is always considered as a positive test charge, mind you, right? And we always say, let's put a positive test charge in an electric field, and where will that charge go? Which direction will it get accelerated? And that is the entire field of electricity and magnetism, actually, to begin with, right? The electricity is completely dealing with this idea of test charge that you're putting at a position and seeing how electric field is affecting it. Okay, and so now when we talk about gravitational field and gravitational test particle, we are talking about the same thing. Okay, we are saying that regardless of whether the moon was there or not there, we don't care. The gravitational field that the earth is creating is always existing. Okay, if something comes in the vicinity of, let's say, where moon was, then it would feel the same amount of force as long as it has the same amount of mass that the moon has. Okay, if there is some other mass there, then it will feel a different amount of force, but it will feel the force always, because the gravitational field is always existing, right, from the source particle that is present in nature. Okay, so that's how we are trying to get to the idea of the gravitational field. Okay, and this field is given by this expression. Okay, so minus mg by r square. Okay, so here we are also going to define the term gravitational potential. Okay, and mind you, the gravitational potential is going to be different than your gravitational potential energy. Okay, and so again, the gravitational potential is again defined as the amount of work done in moving a unit mass from infinity to that point. So now it will be for a unit mass. Okay, and so you can see if there is a unit mass, then your expression for v will become minus gm by r. Okay, and these two expressions are what we are going to use to actually now find the gravitational field and gravitational potential that will be created when we are, for example, using a disk, or when we have a sphere. What kind of gravitational field it will create, what kind of gravitational potential it will create, and uh, when we are actually studying some real problems, we will put some test mass in the vicinity of the field, and we'll see how it moves. Okay, so that's the broader idea. दो मास यहाँ पे बना लो, M1 M2, ठीक है, और मैंने कहा कि इसके बीच में डिस्टेंस R है, ठीक है। सो अगर मैं पूछूं कि व्हाट इज द फोर्स ऑफ ग्रेविटी एक्टिंग बिटवीन पॉइंट वन एंड पॉइंट टू, है ना, एफ जी यहाँ पे क्या है, सो व्हाट इज द वैल्यू, G m1 m2/r² है। क्यों गौरव,
यस सर।
है ना, यही वैल्यू है।
यस सर।
अच्छा, अगर मैं अब इसको ऐसे कर दूं, अब क्या वैल्यू है, और मास सेम है,
तो सेम ही होगा।
सेम ही होगा, श्योर।
सर ये
व्हाट
स्पीड में
अबाउट दिस,
वैलिड होगा ना सर, जी की वैल्यू तो सर।
जी तो सेम है, जी, कैपिटल जी इज ऑलवेज सेम। सी व्हाट वी आर ट्राइंग टू फॉरगेट हियर इज, ये आर है क्या, आर इज द डिस्टेंस बिटवीन दीज टू ऑब्जेक्ट्स, बट डिस्टेंस वेयर, यहां से यहां तक है,
सेंटर ऑफ मास।
सेंटर ऑफ मास, एग्जैक्टली, आर इज कंसिडर्ड फ्रॉम द सेंटर ऑफ मास। सो व्हाट इज न्यूटन डूइंग, न्यूटन ने कह दिया फोर्स इज G m1 m2/r², but what Newton has assumed is that these masses are point particles. That is what he has made. He has made a very, very big assumption. Okay, so instead of this situation right here, if I had removed all of this and said ki this is mass m1, okay, or let me put in a different color. Let me say this is mass m1, okay, this is mass m2, okay, it's only this dot here, okay, still the formula is the same, G m1 m2/r². Okay, so the size of the object and the shape of the object is not considered at all. Okay, he has just assumed that any of the masses that are there, they are just point particles. Okay, and that is a huge assumption. Okay, and he got lucky there, because in the case of a sphere, it turns out that the entire mass is concentrated at one position, and that is the center of the sphere. Okay, so it was a huge assumption, okay, a huge leap that he made, and he turned out to be right. But in reality, we have to consider the size and the shape of these objects, okay, because not always you will see that, depending on the shape, that you cannot consider them as point particles. Okay, so now in the next lectures we have to consider these different shapes. Okay, just like we did before, we have to consider the shape of of your rod. Okay, we have to consider the shape of your spherical shell. Okay, and you can already see that if suppose I have a rod like this, okay, and I keep a mass here at this edge, okay, so here it is seeing probably some mass from this object here, right, and what if I keep the object here, now the field that this object is seeing here will be kind of different than what this object is seeing at this position. Okay, so we have to now create a generalized picture as to calculate the field that is being generated by the mass that is the source mass of that field. Okay, and that is what where we are headed. Okay, so in Newton's case, again, just to reiterate, um, uh, the two objects that he is considering, right, um, he has considered that the entire mass that is distributed in whatever this object is concentrated at one point, and that's what he is doing. Okay, and remember, even the case that we did to calculate the value for G as 9.81 meters per second square, even in that case, what we have done is we have taken the case of your force of gravity, and we said that you have mass of earth and you have the mass of the object divided by the radius of the earth. Okay, so we had considered that for the earth, the radius of the earth is from the center, and whatever the mass is at this position on the surface of the earth, and so we are considering that the entire mass of the earth is basically at the center position here, right, and it's the same problem if there was a person that is standing at a distance r, okay, from a point mass here, okay, and I can call this as the mass of the earth, and I can call this of the mass of the person, and I get the same result. I get the same value, g of m of e. This is the mass of the earth is all here, and m is all here, and then there is re square. Okay, so there is no difference between this picture and this picture. Okay, so what he has done, what Newton has done, he has done a very big assumption. Okay, for example, the sun is creating a gravitational field. If the planets were not there, the field will still be there. Okay, just because there are planets in the vicinity of this field, they are now getting affected by the sun's field, and then they are going around the sun. Okay, but even if the planets were not there, hypothetically, then that field that the sun is exerting would always have been there. Okay, and that is what we are saying, that the source field is always there, and it is coming from certain object, and now we have to see, depending on the size and the shape of this object, what the field would be at all these different positions in space, and then we can give a generalized picture and say that this is the field that is existing. Now you can put anything in this field and we can tell you what that object will do, because we already have the field mapped out, and all we need is you give us the test particle or test mass. We can keep it wherever we want, and we can see how it will behave in this gravitational field. Okay,